Yeah, hi folks. Hi generative AI Bangalore crowd. Right, great to see all of you. Quick intro. I'm Pratyush. I was until yesterday in Microsoft Research. Okay, I was, and then you can ask me what this is. I'll talk about this in the last slide. But I was also an adjunct faculty at IIT Madras. Where I co-founded a group called AI4Bharat. Some of you might have heard it. How many of you have heard about AI4Bharat? Oh, great. Good to see. We have been working at AI4Bharat to build open source Indian language AI. And I'll talk again a couple of slides about that towards the end. Right? So that's a brief intro, and we can discuss more later on. This doesn't work. Yeah. So I have about 45 minutes. We'd like to make it interactive, so feel free to interrupt whenever. Three broad things I want to cover. First is, how do these three things, I think Sachin did a great job to talk about quite a few details about RLHF and so on, but how do these three things, pre-training, fine-tuning, and prompting fit together? And prompting I'm using as a broader term for everything that people are hacking on top of these models. So I'd just like to give you a conceptual framework to think about that. Given my academic background, I'll try to talk a bit about one technical idea you might have underlooked recently that has come out in each of these three things. So the three things each having one key idea. And then I want to talk a bit about what do we do in India for India and so on. Right? And of course, end with what is Sarvam AI and so on. Cool? So these are three things. Please look at them and at the end of the talk, see if you got something. Yeah, so I really like this word trikuti. In Sanskrit, it means three-legged, right? Something that has three legs. And somehow in my life, I always found 3 to be an interesting number. 2 was too small, and 4 is too much, and 3 was a good regularizer, right? And it turns out that quite a bit of things done in India are actually 3 in number. But literally, it means confluence of the 3. And I see the extraction of LLM performance. Right? Many of you are building LLM-based apps, depending on these 3 things, which are, of course, pre-training, fine-tuning, prompting. Right? And I think of this as the full stack of AI. Right? Why do I call it full stack? Because many of us are definitely doing prompting. Right? We go and prompt GPT also on chat.gpt, but we are creating application services just by prompting. Some of us are fine-tuning, and in fine-tuning, I'm including RLHF, for example, that Sachin talked about. And then there's, of course, pre-training. And there are very few of us here doing it, perhaps. How many of you have pre-trained a model? Okay, good. Some hardy souls, good. But very few companies in the world are able to pre-train a model at a reasonable scale, right? But I see these 3 things together, so it somehow goes downwards to up. Few people doing the upper things. I see this as a full stack, and my take is the following. High-value work in AI, work that retains value for a while, will require us to build the full stack, right? And therefore, it requires a slightly more foundational grasp to understand what is the technology that's actually driving this, okay? And I also believe, I didn't write it in the slide, more and more people would be able to do the full stack, right? Already with fine-tuning, many of you are fine-tuning models. How many of you are fine-tuning models? Many of your fine-tuning models, right? And things like QLoRa and so on, they're becoming almost commoditized. I feel we'll get here also very soon. We'll have techniques to make things efficient. We'll have platforms on top of which we can do things and so on. Okay, so that's the thing. And I want to sort of give you some take about how these things intersect with each other. But the key thing is that this is the design space, and we are trying to maximize the LLM performance. Okay, so fine-tuning, right? I'm starting. Is there a question? Yeah.
How do you that be available to all of us?
Yeah, good question. Today, that's the burning question. I'm trying to start a company. That's the only question I'm asking. Where are the GPUs? Things will get better, right? Things will get better from a supply perspective, but things will also get better from a technique perspective. You may not need so many tokens after all. At least there's one thing that I'll talk about, which is that the cost may come down, right? Yeah. Any other questions? Okay. So fine-tuning, all of you have studied machine learning, I'm sure. This is the more classical machine learning, and it's in fact very important to see how we are deviating from classical machine learning with LLMs. And I like to bring that analogy here. In classical machine learning, you give me many x, y tuples. X is the input, y is the desired output. and I can train something like a neural network that approximates the function f of x equal to y. This function f will be my neural network. I mean, for something like a series of health indicators and efficacy of a treatment, this could be just numbers, this could be a decision tree, for example. For something a bit more complex like reviews in Amazon and the corresponding sentiment, it could be an older generation neural network without even transformers. For something like a sentence in Hindi and the corresponding translation in English, it could be a transformer model. But notice that all of these are simply based on x, y tuples being given in huge volume and training a model, right? That's the machine learning paradigm. You give it these outputs and you train something, right? And all of these work before LLMs, right? This is just this leg, the fine-tuning leg of our performance, right? But if I give you a 20-page judgment, a legal judgment, and I want a one-page summary of that, right? It turned out that the previous generation of AI models weren't very good at it, right? There were summarization models, but they were not very good, right? Now, why is that? Anybody wants to say why is that harder problem?
Lack of quality data as inputs.
Lack of quality data, yeah. So the number of XY tuples I have, that's much lesser, right? Okay, anything else?
Harder to do one-to-one mapping?
Harder to do one-to-one mapping, can you go a bit deeper?
I'm not an engineer, so
Okay.
I'm just...
Okay, I'll let you out. Yeah, maybe hard to think of what, yes, there's a hand up. Lots of? Possible y's, yeah. Maybe it's related to what you're saying, which is for a given x, there are many y's. And how do I know what is good? How do I know what is ground truth, right? Cool. Okay, let's think a bit more. A philosophy major question and answer to that, right? This is harder in a different sense, right? It's harder in the sense that there is correctness that is required on this, which needs to be grounded on a very complex set of human knowledge, okay? Given a topic, write a sonnet, okay? Many people until 18 months back thought that this is creativity and machines can't do it and so on. So clearly you can't give XY tuples. We didn't have so many sonnets, by the way. Probably we do have now, but this is very hard, okay? But I just want somebody to volunteer to talk about what hardness means. So we have been seeing this. We have been seeing XY tuples. You're able to get a sense of hardness. But if you think about, yeah, you have a question?
No. My take on hardness is they have to have a world view, have world knowledge that is ultimately in some compressed form lying deep inside of them.
Cool. Okay. So the input here is that to solve this, you should know what life is about, right? Something like that. Then you can write good sonnets, right? Okay. Yeah. Point taken. How would you characterize hardness? Can you take a formal grasp at it? Formally, what would you say? Yeah.
I mean, ultimately, some measure of like compression in terms of how much you know about the subject to be able to like, unfold it to whatever the problem is. So,
Compression, can we be precise? Compression of what to what?
As in the whole approximating the data set you have to figuring out.
This is what we have. We have X, Y tuples, right?
Yeah, I mean, even approximating, let's say if it's writing a sonnet, what are the essential properties of a sonnet? So, really learning that itself is...
I see. So you're saying that Y needs to be well formed, even understanding what a good sonnet is. That's very hard, okay?
Yeah, for a lot of problems that now are getting cracked.
Okay, good point. Yeah. I'll complete, yeah.
Formal mathematical way of looking at what like goodness or badness is, right? Isn't it sum total of all humans, like measurement of that, and then you average that in any capacity, and that is like how we define good and bad?
Okay, this sounds philosophical. Is that formal or?
Mathematical.
Okay, I'll take it, yeah.
Much higher number of dimensions in the output.
So how would you characterize that? This is sonnets, right?
So
this is text.
In the earlier case of translations or prescriptions, there is certain like dimension of data and knowledge you have to put. There are like much more dimensions which need you to have like a complex vector.
Good thought, but dimension of what? Just think about that, right? Yeah.
There are a lot of patterns
Who's
from
speaking?
X to Y mapping, like.
I can't see who's speaking. Can you just, yeah, okay.
So there are a lot of patterns when we convert we take all the x parameters and convert it to y. So
Okay.
it depends on number of patterns. Like
Number of patterns, something about dimensionality. Yeah, last answer.
The space is too vast and not very well conditioned, because if you move a little bit, it's not a solid basically.
Okay, good thought. Space of what?
The outputs, the inputs, and the functional space itself.
X is any topic, so X is not so well conditioned. Right? It's not particularly constrained. I could write a sonnet about you, right? But Y, yeah, Y is constrained.
If y has to be optimized on multiple variables,
Hmm.
then that would make it way more like the complexity. If it's arising with like the output has to be optimized on many different variables, and that would make like multivariate problems can be of many kind. But like if the output also needs to be multivariably optimized, then that would make it more complex for this
Okay.
thing.
Sometimes you said you're not an engineer or something, right? Okay, I'll not go there. Okay. Okay, so why is this a hard problem? We've been discussing this. How do you define? I would like you to think of it as an optimization problem. Right? The key thing is you're worrying about x and y spaces, but our intention is to train a function f. We are doing an optimization, right? And a simple optimization is something like this. You have y and x pairs, and you ask, can you fit a line to some data, right? That's the simplest thing you might have studied, linear regression or whatever. And you need to think about difficulty of this versus difficulty of fitting a quadratic, right? What's different between these two? The number of free variables, right? Of course, this can also model lines, right? But it is more expressive, but it needs more free variables. So a good way to talk about difficulty, right? Though I'll tell you we can't do it, but at least a way to approach it conceptually is to think of what are we optimizing and how many free variables I have to optimize that. Okay, so this thing here, one thing to notice is that at this point, I might have data, but it's actually, let's say it's a linear data, but I fit a 10-dimensional polynomial on that. I mean, that's a bit stupid because the dimensionality is not 7-dimensional, it's just still 1-dimensional or 2-dimensional. I'm just not aware of what that dimensionality is. So one way to think about it is what we call intrinsic dimensionality of an optimization problem. Okay, you're optimizing something, you want to understand what is the dimensionality of that space on which you should move things. How many free variables should you move to get to the right answer, right? Ideally the optimal answer, but because this itself is an optimization problem of computing the intrinsic dimensionality, we would say get up to 90% of the accuracy. Okay, just to repeat this part, you have a problem that's typically much more complex than this. It's neural networks here, not linear or quadratic functions. For them we ask, how many free variables should I move such that the result is up to, let's say, 90% of the optimal result. Okay? All of us, yeah, question?
Is it just the number of free variables or even the interaction between them?
That gets even harder. We assume zero covariates or whatever. We assume they're independent and we try to optimize. But they are not in reality, right? They do all interact. In fact, optimization algorithms interact between variables. But at this level, it's just how many free variables we have.
I think what I'm asking, architecture also matters, right? Like in some sense, this
Yeah.
linear and that's a quadratic, and that also matters apart from number of variables.
Correct. So you're saying, hey, I might not choose polynomials, I might choose some constrained functions, and what constraints I choose on the functions will also affect it, granted, right? You will see that I'll start formal and then leave all formality. I just want to give you intuition, right? I'll just get to that point. Anything else? Yeah.
What was the X5 layer before? Like
The X5 pair before was a topic and write a sonnet.
before this?
Before this, it was a philosophy major question and answer.
How are the two different, like in terms of that hardness?
I wanted you to approach it from your perspective, how you think of hardness, and realize that there might be many different ways of thinking about it, but mathematically they may be still the same. Right? So in fact, if you see, this is about getting lots of domain-specific things. This is something very correct. It has to be correct in a particular way, and this is creativity and all that, right? So, yeah.
What about convexity or non-convexity of your objective function?
Deep learning guys don't talk about that word. Okay, they have left all those things like convexity far behind. We just assume you could get somewhere.
For example, if you look at the loss landscape for
Yes.
ResNets versus the standard convolutional neural networks,
Yes.
you see a much more complex loss landscape for the typical convolutional neural networks as compared to resonance. It's because of the skip connections that we have in resonance, right? So even in a way, as he mentioned about the architecture that we choose also improves your chance of attacking a complex problem, while even the objective function in itself would lead to various complexities or in a way define your hardness, because you're assuming a form for your function space in which you're going to search for free variables. Right?
Very good point. In fact, ties to the point about relatedness of variables. With skip connections, for example, people realize that it's good to train certain variables together and have a gradients passing through them in a correlated way. That works, right? And interestingly, the last decade in deep learning was about finding such structures and what works better for what domain. For whatever reason now, for a while, we think transformers are solving all problems, right? This notion of a multi-headed attention seems to be doing quite well. In fact, I don't think that's a final thing. They will find interesting things. In fact, multimodal might require completely new ways of thinking about things. But for some this local period that we are in, transformers seem to be the choice we make. Right? Okay, let me move on. Yeah, we are talking about hardness, and I was talking about this notion of an intrinsic dimensionality, which is the number of free variables in the optimizer that you want to optimize to get to a reasonable solution. And how big that number is tells us how hard a particular problem is. Okay. So for example, take this particular input amongst the many questions that we had. This thing we would say that the ID or the intrinsic dimensionality is huge. That's why we are not able to solve this, right? If you gave x as some vector, y as some vector, and you took a neural network and you said go change how many parameters you want, you'll have to change many parameters, millions, billions of parameters to get to a good solution. Assuming first of all you had lots of xy pairs. Okay, intrinsic dimensionality is often, of course, related to how much data you have, right? And you would need lots of xy pairs. So, what does that have to do with the second leg, which is pre-training? Okay, and this is, I think, a key insight. And the paper that I'll cite is something that is hardly cited, but I think it's one of the most important findings of deep learning in the last few years, right? Which is that with pre-training, if you train a model to predict the next token. I think all of you are aware what is pre-training, but you take a large amount of text and you train the model to keep predicting the next token based on the previous tokens. There are variants of this, but let's say you're doing it causally. And you could have things like 1 to n tokens, and you predict the n plus 1 token given the previous ones. This is what is pre-training, okay? And the advantage is I don't have to go create XY pairs. I have XY pairs in Twitter, in Reddit, in Times of India, and so on. Right? Of course, these guys are shutting down now, so we'll have to figure out what to do. But there are these XY pairs there. Okay, that is pre-training. Now, the critical thing is this: if you pre-train a neural network on trillions of tokens, then it turns out that if you took this network that is pre-trained and then try to fine-tune it for XY tuples, okay, for some task, could be the sonnet task, then you significantly lower the intrinsic dimensionality of solving that task. In other words, took a neural network, if you took it from scratch and tried to solve this problem, it has a huge intrinsic dimensionality. But if I pre-trained it, conditioned the neural network, and then tried to solve for this, the number of free variables I now need to change is much, much lesser. Okay? And I think you can intuitively see this is why this is, but this was a paper, I think it's in 2020, before all the hoopla, but it has only about 120 citations, okay? And academics would say, hey, this is not well cited, right? But this paper talks about intrinsic dimensionality explains the effectiveness of language model fine-tuning, okay? And there are two plots I want to show you. It's not a paper with nice looking graphs. That's also maybe the reason why it's not well cited or whatever, but these two graphs are very important to understand, okay? So let's take a couple of minutes to understand this. Here you will find on the y-axis D90. D90, think of it as intrinsic dimensionality. Formally it is how many dimensions to change till I get to 90% of the best solution, right? So somebody is actually taking a model and saying, let me change 1 parameter, 2 parameters, 10 parameters, and so on, and seeing if you get to 90% accuracy. At the point you get, you call that D90. Okay, so you're doing a search at each point, right? So this is D90 being plotted. X-axis is plotting number of steps of training a Roberta model. Again, a model that has gone out of favor. All of you are aware of BERT. How many of you have used BERT? How many of you used Indic BERT? Some of you? Okay. We built a Indic version of Indic BERT. We got about 100K downloads, and Hugging Face, we don't know who these guys are, so I'm just wondering if some of you downloaded it, right? Okay, this is an older model, Roberta, and what somebody's doing is, let's look at any one of these lines. These lines are actually different data sets, right? Think of them as different sets of XY pairs. For example, MRPC is some paraphrase data set. You're given a question, maybe Quora question, you're given another question. And your job is to find out, is it a paraphrase or not? Right? Because if it's a paraphrase, I can show the same best answer for the previous question. Right? And there are other things, like for example, Yelp is some review data set, this is some sentiment set, and so on. So there are different XY pairs. So look at any one line. Let's take this blue line here. What this is saying is, if I took a Roberta model and pre-trained it to about 70,000 steps, and then tried to compute the intrinsic dimensionality of getting paraphrase right, then that is almost 5 into 10 power 6. Okay? So I need to move many variables to teach it paraphrase detection. Okay? Which means I need many data points to teach it, right? But as you train Roberta, this thing falls down dramatically. Okay? To the extent that at this point, I don't know if this is large or small, 200K steps, you are at 1,000. Okay? I just need to move 1,000 numbers in that huge Roberta model to actually get it to do very well on paraphrase detection. What is happening with GPT is we are somewhere here, I don't know, outside the room, too many steps, and these things are close to 0. You're able to say, I'll give you a new task. GPT has never seen that. For example, I'll say, write me a piece of code and generate comments in Hindi. Okay? Never seen that task, but it will do that. Why? Because the intrinsic dimensionality of that is almost close to 0. The model as it is can answer that. Or you might have some customer care problem, and you may say, I'll give you 5 examples of how you should answer in the prompt, and you try to answer. In some sense, you're saying 5 examples are good enough to train it. You're not training it explicitly, you're giving it in the prompt, but I think it's a good metaphor to have in your mind. Okay? But this is superb, right? You're actually seeing somebody actually prove what's happening with pre-training, that these intrinsic dimensions are falling, and interestingly, though this is next token prediction, all these curves are falling. So multiple tasks, diverse tasks, some on sentiment, some on paraphrase, are all becoming easier because you are doing next token prediction. Okay, I'll take a break here. Any questions at this point? Yeah.
Is there an explanation why?
Yeah, now we get philosophical, right? So we're talking about world knowledge and so on, right? I mean, that's what it is, probably. It's just, it knows lower dimensional mappings from a very broad set of inputs on which it is able to do optimizations, right? In other words, language is very high dimensional, but meaning perhaps as a hypothesis could be much smaller dimension, especially for things like paraphrase detection, and it is able to find those lower dimensions, and a search for intrinsic dimensionality is able to search for that low dimensional space and discover those parameters. Yeah. A bit louder, please.
Earlier you mentioned that in this local window today, you need to transform model the answer. But if you go by this paper and the IT problem statement, typical neural net theory, why would you say that? It seems like it should solve for everything.
Sorry, this should solve for everything?
Yeah. This approach, like why would transformers in that case be a local in time today for solving most problems? Because from a neural net training, this is pretty intuitively now seems in rear view but obvious, but then the forward also seems obvious that this should solve even the multimodal problem.
This is sufficient but not necessary, right? It works here, but is it necessary? We don't know, right? There might be another nice little architecture hiding somewhere we haven't found out, and unfortunately, it's very, very expensive to go search for that, right?
Just a small question. I mean, it almost sounds like we're building a case for larger and larger models versus smaller models. Given, if you play
The case has been made. I'm just saying why. That's all.
So, what's your point of view on smaller versus larger models?
Yeah, this is clear. This picture is very clear. The gradient is negative, right? So as you go larger and larger, I mean, it is not exactly. In fact, the next slide is that. The next slide is exactly what you're asking, which is this slide was about pre-training more, right? So we are talking here about as it sees more tokens, what happens, right? But the next slide, again from the same paper, is if you increase the models, and they did a good job to take all the good models of that time. This seems more like a I don't know, a symmetry of models now, right? All these models came and went. But at that time, these were models that are very popular, T5 from Google, for example. And as you increase the number of parameters, please note this is a log scale. So it's really 2 orders or 3 orders of magnitude, whatever. What you find is intrinsic dimensionality falls, right? So as you go to larger models, 2 things happen. The ID falls, but in the paper it also says that the point when ID is small, the number of steps or tokens it should see also falls, right? So paradoxically, you take a large model, train it for fewer steps, and you get to a better world knowledge model than taking a smaller model and train for the same number of tokens, right? So that's what also the paper establishes that. But I have another take on small models. I'll come back to that later.
How did they determine ID?
Good question. And that's a bit of a technical thing in this paper, which is you take this model here. This is a 6,000, 7,000, 70,000 step model. And then you search for D90 by saying, I want to go take random parameters in the network of so many D90s, let's say 100, okay? And then try to change them and see at which point I'm able to get to within 90% of the best known results, right? The problem here is you have to make a choice of which parameters, right? And they make some low rank assumptions. They say that I'll take a fewer parameters and project them onto the entire network, meaning I will have only 100 parameters, but I will multiply it with a matrix which makes it 100 million, for example, and add it to the 100 million network. Okay, that's a bit of that's commonly done in compression, and then they repeat that for every D. At the first instance, when they hit 90%, that's D90. So this chart is very expensive, right? Somebody has burnt out of compute to compute this. Yeah.
For pre-training, what's a better trade-off, having multiple passes on the same data set with smaller learning rate, or like just one pass over a very large data set?
Yeah, I don't know. People, what they have been saying is too many. I mean, people have been doing either 1 or 2 epochs, right? In practice, they have found that if you do more, it tends to exactly memorize, which is a problem from a PII perspective, toxicity perspective, and so on. But I don't think we fully understand that. If we had more high-value tokens, perhaps you would do many more epochs, right? So I have some thoughts on that.
So this particular plot, it does not count for the size of the pre-training corpus, right?
So now what we are finding is even smaller models trained on a larger corpus are doing better. So
yeah.
Then if we go back to our initial formal setup we had in terms of the number of variables we have and all those things,
yes,
all that is not counting for the pre-training corpus we have.
Good question, but this guy is super tiny compared to what we are talking about now, right? So in other words, yeah, I mean, you could do this with 7 billion and exactly see something where it actually falls much faster, right? So the small and big of today are very different from that. So there are more hands coming up, right? So how am I doing on time? 3-0.
Yes.
Okay, that sounds long enough. Yeah.
So, according to you, like, does it make sense that today we invest time and money to in pre-training or fine-tuning these models, or just let the time do its job and we will have smaller model which does all domain, and there is no need of domain-specific or task-specific training, like?
Time will do its job in the sense that other companies will do their job, right? That will happen, and many things will get discovered. But I believe in small domain-specific models. I feel that that's a value add. Yeah.
Would this also explain your emergent in the models? Is there a link between
intrinsic, dimensionality, and emergent properties in the models?
Exactly, right? Emergence is very hand wavy. This is less hand wavy, right? And what is emergence? We just say that, okay, we didn't expect it to happen, right? But there was a paper 2 years back, 3 years back that said that, hey, the dimensions are going down, right, to train them. And you will, what we didn't know, these are actually, frankly, in today's time, very toy data set, toy tasks. What we are finding is you can go to really complex tasks. That we didn't know. Can you write sonnets? Can you write code that is 50 lines, 100 lines? That we didn't know.
So, but the question really is, what things are we missing? Are there any emergent or all this intrinsic something that we don't even have a data set of, right? Or what other hidden emergent properties are there in the language models other than? Do we really know that?
That's one section in my talk, so I'll come to that. Okay, let me move on. So I hope that you got this, and I really would like you to feel that this is a little bit of an aha moment, right? So you now understand, hey, we have been doing pre-training. What we are really doing is building a model on which I can train for new tasks with much fewer parameters. And that's what is happening, right? And if you take that to the extreme, the emergence kind of thing, huge models, then you can even do that zero shot. That's what's happening. Of course, that's not fully true because you have to combine the two legs. You can't just say pre-train and then do zero shot. You have to combine pre-training and fine-tuning, and people are doing that, right? If you fine-tuning at least Llama 2 clears all the problems coming from Lima, Vicuna and all that, you actually have to fine-tune properly. You actually have to do SFT, RLHF, we just talked about RLHF. So you have to do all of those things. But the combination of these two means that something like this, which is 20-page judgment to 1-page summary, very, very hard in the yellow world, is now possible in the red plus yellow world, very easily, right? So easily that this is definitely a commodity. Nobody will build a startup to do this, okay? That's important to appreciate what just happened, okay? Of course, writing sonnets and so on, that seems to happen. So I just want to also leave you with a little bit of an analogy. It just helps me, maybe it helps some of you, which is that I think of pre-training as fitting for an environment, okay? And I equate that to humans having gone through evolution. Right? What have we done in the billions of, I don't know, millions, I don't know how many years we are there as a species? We have been going through small changes to fit ourselves to the environment that is around us, right? And how do we specify the environment that a large language model should see? We give it data from Times of India, Twitter, Reddit, and so on. That's the environment. That's the text environment of the universe. And we are training it on that. And the consequence of that is you can now teach it new skills by giving it 5 examples. 10 examples, okay, or 25,000 examples, and that's what we are doing at school, right? I mean, you've been pre-trained for a long time as a species, and now you come to school, you understand division in a week's time or in a month's time, depending on whatever your mileage, right? And that's what is happening, because some people used to ask earlier, hey, why is deep learning so expensive? Why do I have to teach it with tens of thousands of examples when humans understand it much lesser, right? I think this is an answer. Right? People will still complain and say, this is very expensive. I mean, humans understand very easily. It's not true. Your genes have evolved forever to really be good at what they are doing. The, I don't know, elephant is not doing it perhaps, or the cockroach is not doing it, but we do it. Right? And I just see this as an analogy for me to understand this, which you can take this a bit further and ask, are you building a human brain or a cockroach? Somebody asked about domain-specific models, right? You can actually ask, for my task, I don't need to build a human brain. Maybe OpenAI is doing that. But for many of the practical things, you want to build specific instances for specific skills, and you may therefore think of other ways of doing it. Okay, a bit of philosophy, I suppose. But this was the next question that somebody asked, right? Can pre-training only work with billions of parameters? Is evolution the only model that we have, right? Or a global evolution? And here the answer is depends on what the environment we are trying to fit for. Right? If you actually simulate a different planet with different conditions, perhaps it will evolve in 10 years. Right? Maybe Earth is too complex to evolve. In fact, most RL experiments that we do in small environments are about fitting an agent to a small environment, fewer rules, and it evolves in few thousands of generations, for example. Right? So it depends on that. And there are 2 works, some of you might have seen this, a bit more popular in the press, but I just want to bring them up. I think they are important papers. One is, it says, tiny stories, how small can language models be and still speak coherent English, by colleagues from ex-colleagues from MSR. They show that you can actually train a model with tens of millions, not billions, tens of millions of parameters, and can generate good quality English as tiny stories. Okay, so if you have an app that's building stories for kids, want to put it in a doll, it'll tell you a new story each time. You don't need a billion parameter model. You can actually do it with millions of parameters, because you can go and so what do they do in the paper? They say that it's very important to ensure that your pre-training data is aligned with your final use case. Right? Typically, we don't do this. We say pre-training is some global thing we do, and then we start making specialization later on. But pre-training data can be specialized for a use case. And what they do is they generate pre-training data with GPT-4 of a particular nature, constrained by structure, but diverse enough that it understands world knowledge, understands emotions, understands reasoning, and so on. So this balance is important. You want to have narrow structure, narrow domain, but fairly broad enough that fluency of language comes in. And this shows that writing at least fluent English is not as expensive as billions of parameters. Okay? Maybe it's in the millions scale. And this was to your question, right, about hey, GPUs are scarce and so on. Maybe there are a million parameter models hiding somewhere, which we have to discover. Okay? This was also followed by another paper which took inspiration from that. You might have seen this one more. It's called "Textbooks Are All You Need." A very misleading title for what the paper is. I think it's here. It's for programming questions. Typically things like you will write a doc string and ask you to write a Python program. That's one particular data set. On that data set, they were able to show that you can train it on billions of tokens, not trillions. The previous one is about how big the model is. But this is about how big the data set is. You can actually do it on billions of tokens. And therefore, I think, how much is it? It just says here, 4 days on 8 800s. How many of you have 4 800 days with you? 800 days. Okay. We are relatively poor. Okay. Okay. Yeah. Maybe write a paper with even smaller numbers. I think it's possible, right? So I would say is the second thing, and I just would like to highlight that we don't think of pre-training as a design variable, right? In things that we do, I think it's worthwhile considering that as an option. You want to build something for customer care, you want to build something for, I don't know, healthcare or programming and so on. Can you start thinking about creating pre-training data sets? And what you're doing here is the following. You're saying, I'm going to pack more information content per token in my pre-training data. Rather than giving it all the crappy code that some intern might have written in some GitHub, you don't want all that. You want to think of high quality pre-training tokens. It should be constrained by form, but diverse. It should understand the full of Python, right? It should be diverse enough. So how do you exercise the generative power of these very, very large models and generate that kind of data is an interesting problem.
So is there a systematic way to think about this data set creation for small models?
Yeah, that's something that this paper goes into some detail of. And one thing they say is, see, what do we do when we teach kids? We create textbooks, right? And therefore their hypothesis is, think of it as creating textbooks, right? What do textbooks have? They have structure, they have coverage of all the things, and then they have some pedagogic elements, right? They would teach it to you in some steps so that things build up. They'll have an example that is running and so on. If you think like that, it gives you some angle at approaching that problem, right? But maybe there are other angles, right? For example, the other paper does something different. This one, they say, okay, I'm going to have lots of topics, and I'm going to try to write stories on each topic, and I'll have multiple characters, and I'll have different kinds of endings and so on, and I'll span that space in the data that I generate, right? So some notion of coverage is important.
Sort of like creation of curriculum, and then...
Curriculum is a good way to think about it, yeah.
I remember arguments from like 5-10 years ago being able to speak fluent English, so why is this different?
I would like to use that model. Which one is that?
I mean, this is toy models from
Okay. I'm happy to look at that, but I guess they would be in a smaller domain. This is writing stories. Okay. The way this works is, you write the first 2 lines, Jack went here, Jill went there, and full stop, and it completes the story for you. So it's a bit maybe more than writing text. Anything else? Yeah. two things. You can write papers and Microsoft can do it. Right? There's some value in early investment, right?
How is this different from like fine tuning? Like ultimately, it's just fine tuning is here and your like general data is here and what you're doing is something over here, right?
Good question. That's exactly what I wanted to trigger. I wanted you to trigger the thought that next token prediction can be thought of as specializing for your task, right? Of course, the objective function is very different, and that's the beauty of it. It's a very generic objective function. But if it contains the domain's knowledge, that's useful, right? So I wouldn't call it fine-tuning, but it's just packing more about a certain domain, but training it with a different objective, so that it learns those lower dimensional maps and so on. Yeah. Okay. Great. So second idea. So opportunity to generate diverse, high-quality, domain-specific subsets of pre-training data. It also means that certain kinds of data available in the world are more valuable than other kinds of data, right? Textbooks in particular are very valuable, okay? Or anything else where humans can actually spend time telling you what is valuable and what is less valuable, as opposed to just taking a broad sweep and taking data from everywhere. That's going to be a value add. All right, and then I want to come to prompting, the final leg, which many of us are doing, completes the story, completes the 3 legs. And again, a bit of analogy, right? Even after evolutionary optimization, careful education at school, still we may not get the desired performance at the workplace. Okay, so you really need. So you have evolved a long time. You went to I don't know whatever college, but you go to your job and you learn at the job, right? So this is the zero-shot training that all of us are doing. And the interesting thing is there are no very solid cookbooks there. There are some cookbooks on the web, but it's still something that we are trying to figure out, just as we are trying to figure out how to motivate all of us to work, right, and so on. So let me talk a bit about this, right? So we have fine-tuned a pre-trained model. We have reduced the ID with pre-training, and then we have fine-tuned it with XY pairs. Could be SFT, could be RLHF, doesn't matter. It's just different variations of this. And then now the question we are asking is, are there other types of X? Let's look at the question. It's an important question, an unusual question in machine learning. Are there other types of X where the model is already good? Somebody asked this question, right? Which is, I thought I fine-tuned it for some XY pairs, right? But is the model already good for something else, which I don't even know, right? Again, machine learning has been driven by telling the model do X to Y well. That's what we do, right? But with pre-training and with fine-tuning, mainly with pre-training, we might be creating a lot more opportunity to solve other tasks which we haven't even thought of, right? I'll let you reflect on that. And the second thing is, are there specific ways of writing X so that I get, this is the wrong spelling, of course, the right X, the right Y, okay? Can I change X to get my Y? Again, please reflect. In machine learning, X is thought of as the unchanging input. I want to improve the model to get the right Y. But with prompting, what we are saying is, X is a design space, right? If I change X, I'll get the right kind of Y. Maybe there are X's that I can choose that I didn't even know. Maybe you'll discover it next year. But even for the X's that I want to write, I could write it differently and get a better Y, okay? This is because, of course, pre-training may have reduced close to zero the intrinsic dimensionality of many, many tasks, okay? And important to appreciate that this is a highly unusual problem in machine learning, as I just said now. Okay? And there are 2 papers. These are crossing the 1,000 citation mark, so they would be considered popular papers, but I think they may not be known to you. How many of you have seen this paper? 1, 2, okay. So this paper says, this is from, so I think 2020 or so. Percy Liang is a professor in Stanford, I think someone you should follow. Prefix tuning, optimizing continuous prompts for generation. This is pre-GPT, right? But what they are saying is the following. Let's say this is the transformer that is getting different tokens for doing translation, right? And these tokens are something like, translate the following sentence to Spanish, : right? Sentence. This is what these boxes mean here. Or summarization. Summarize the following as if a 5-year person understands this, right? And then paragraph, and so on. Now, what they found you could either give this model, this to the model, or you could say for each of these tasks, things like translation, summarization, table to text, I'm going to say there are few empty vectors. I won't write those words myself. I'll use machine learning to go search for vectors which will do that task well. Okay, in other words, I don't want to write the prompt. I don't want to write X. I want to say there's a part of X which I can specify as vectors, and I'll go search for the right vector such that the answer is a better translation, a better summarization, and so on. In other words, you want to, given the model, given that it is pre-trained, given that it's fine-tuned, you want to optimize the prompt by searching for it, as if it was some machine learning continuous input. That's why the word continuous prompts, right? We think of prompts as discrete in natural language, but you can think of them as continuous in vector space. And they show excellent results, right? You can learn a task-specific description that gives the best performance for that task. I didn't include a results plot, but you can go look at the paper, right? Another paper, I think around the same time from Google Research, which is the power of scale for parameter efficient prompt tuning. And this plot may be interesting. Here they have something which says, okay, I took some models. I don't know what model. This is D5 model. I increase the number of parameters, but just look at one such vertical line here. This is some performance on some NLU data set. And what they say is, I can either model tune, I can take the data model and fine tune it for that task, or I could do, I don't know, multitask fine tuning. Sometimes it turns out that if you want to solve task T, then you may also train it for task T prime, T double prime, and so on. Or you could do prompt design, which is what people are doing. They're rewriting it manually. Or you could do prompt tuning, which is go search for vectors in an automated way. And what they show is, as the model becomes fairly large, it turns out prompt tuning is competitive with model tuning. I give you a pre-trained model, I give you some new task. Instead of tuning the model, I may as well go and just search for the right prompt as if it was a vector, not a set of characters. Okay? And that's competitive, right? And in fact, this is a hack that many of you must try in things that you're doing. Definitely, we are far to the right of this with the current models. Can you think of putting some vectors there and searching for them to do better in your task? Question on this?
Hide seems similar to this in the vector DB world too.
Sorry, can you repeat?
Hide, which is like hypothetical data creation.
Document.
Okay.
Yeah.
Hypothetical document is there. So
Okay.
It's sort of like rather than imposing your question into the vector DB model, you change your question into the text that the question would have, like the summarization that would have answered the question, and then you search for that summary. So it's rather than searching for the question, you're searching for the answer that the question implies.
Yeah.
And you end up getting much better vector DB hits.
Yeah. You're right, but that's a different idea. So the question was, sometimes it turns out, let's say, I had a question like, what is photosynthesis, suppose, right? Then what do you do typically today with the retrieval augmented generation? You would say, I'll take this query and I'll search in some semantic database and try to find an answer. I try to find not an answer, but a piece of text and bring it here and then generate the answer. An alternate way would be, how to do, what is photosynthesis? You send that to a GPT 3.5 turbo model or Llama or whatever, get the answer, and then use the answer as the key to search in the database, right? So instead of doing a cross embedding search, you could do same domain embedding search and try to find the nearest neighbor. So slightly different idea, but it's something similar. You ask the model, instead of you fine tuning it, you ask the model to find a better prompt. Yeah, question? Yeah. I mean, you could look at these papers, but the basic point here is that these are just vectors. Think of it like, hey, I'm going to put in 10 tokens, which are just bytes, okay? And I'm going to search in that space, right? So it's not a discrete space. This is going to be a continuous search, and you may use various things. You may do hill climbing, or you can just do sampling and things like that.
So essentially, this is replacing the tokens embedding vector with some continuous
Correct.
search thing, right?
Correct. Which could be gibberish in our world.
Yeah. So is there like a guidance on how many tokens do you generally end up replacing for searching?
I haven't done this myself, so I don't have an intuition on that, but we can check these papers, how much they do. Right?
But that's also design choice.
It's a design choice, right? And I think this is really the thing of, here is a language model, and there was this meme that came out very early, right? We don't know what the beast is. Right? We're talking to it in English, but there's some beast inside. And this is really saying that I want to translate from my language to the beast's language, right? And you just want to learn.
think something similar came out yesterday with adversarial continuous prompts.
Okay.
Where they were able to break the safety of these models like GPT-3 by appending some gibberish that they found through.
Yeah, can imagine that. Yeah. There are side channels to talk to the model, to the beast. 5 more minutes. I'll just go faster. I'll just stop this part. I think you got a sense. I think these three legs are to be thought of as together, and some things which you may not think of as design variables are actually design variables for you to look at. Prompting and pre-training data is not a design variable. Typically, it's actually a design variable. Prompt is not something that you optimize, but maybe you can optimize. So please think of these three things together as you try to extract performance from LLMs. Okay. Now I want to switch tempo and tenor and intent and talk a bit about what can we do for India, in India, and so on. There are some interesting plots which are missing. Okay, but let me just draw it for you, how it would look like, right? So imagine a picture following my hand which says this is the quality WEC or whisper, some model that comes up, there's a step change and keeps improving. Then the corresponding Indian use cases will typically be somewhere here, and they'll take a long while to catch up, right? To just get the best ideas that have been proven for, let's say, English to Indian languages has typically taken very, very long in the older generation of AI, right? And why? Because, of course, it's very simple. It's capitalism, right? There's not a big market for Indian language AI. We are a big market in terms of number of people, but in terms of people actually consuming Indian language AI, it's a small market, right? Increasing by the day, but that's the nature of things. The problem with LLMs is that, again, nice plots are missing. The step change is much, much larger. Okay, you suddenly have moved the AI field so much that researchers don't know what problem to solve next, right? So they don't know what to do. It's not clear. We don't understand these models at all. So there's a huge step change, and there is the case to be made. How do we catch up for Indian languages, right? Because the step change is so large, the inequity that is possible can be large, right? Not in this room, but think of somebody in Bihar, think of somebody in rural Maharashtra. They would like to use voice, they would like to use their language, and they would like to interact with all this LLM goodness, right? They would like to become better programmers. They would like to understand, maybe, I don't know, Ayurveda better, or they maybe like to learn their textbooks better because you have models that are good, right? So the question was, how do we do this much, much faster, right? And we took up this problem for the older generation of AI at AI4Bharat. It's an academic body at IIT Madras. Mitesh Kapra is a professor, and I started it. Vivek Raghavan was standing somewhere. He's not standing somewhere, okay. He was the one who sort of mentored us, and this was our intention: bring parity. You're here, okay. Good. So bring parity in Indian language AI with respect to English, with data, models, and tools all in the open source. Right? This part is important. It's a small pie. We need to increase the pie. So let's do things in the open source. So you will find that you can go to ai4bharat.org. You will find lots of data, lots of models, and lots of tools available completely in the open source. For example, we have speech recognition models for a variety of languages. We have translation models. We have tools to collect data. We have data sets. We have, for example, Indian language tokens. There are 20 billion of them, and so on, right? And in about 2 years, we made some reasonable progress across few axes. And different places that I go to, I always meet people who are using what we built in some way or the other, right? And let me just tell you 2 things that we have done. One is translation. Again, slightly complex picture, but let me help you with this. This is translation, and what you're seeing is some metric of goodness of translation from English into one of these languages. There are 22 languages here because the Constitution of India thinks there are 22 important scheduled languages. Don't ask me who made this choice of these 22 languages, but different models mentioned here. And as you can see, in 2020, Meta released an open model. These are all open models. Hindi was somewhere here, but there are many, many languages doing quite badly. For example, Telugu was for some reason doing super badly. And we released a model 2021, and we pushed the needle for a bunch of languages. We didn't work on these languages. We pushed the needle on a bunch of languages. The accuracy became much better. Then Meta strikes back. Okay, so they wrote a paper and they little bit moved it because notice this is open source. they can take the data that we created and leverage that. And that's what we really intend to do. So they moved the needle a little bit on these things, and then we released a second model this year. And you find that first thing is that we have moved all these languages up, and they are all here. So something like 60 is pretty good on this thing. This is a character-based metric, because Indian languages is a bit trickier to do with words. And we have moved the language here, and the size of this is the number of people who speak that language, right? So this is the kind of impact that you can have, right? And it turns out that our models today are not only comparable to open models, but also models from Google and Azure. In fact, we are doing better than Azure almost always, but also are comparable with Google. So there's an open source translation model that you can use for Indian languages, both from English to Indic and Indic to English, which is actually better than, or at least equal to, every other model. Right? And you can do this in 2 years. Right? If you have the intent, go after data, collect it at scale, you can improve things. Similar story for speech. I won't go in details, but we have been improving what is called the word error rate, and we have been moving things a bit. Far fewer languages, because the data in speech is much harder to get. And it turns out that today our models are actually better than Google and Meta and Azure in speech recognition. You speak and I want to transcribe it, the best model is here. In fact, I met some people yesterday, they're using it in all kinds of startups. Ola is using it and so on. Okay. But this is the last slide. Okay. But with LLMs, it looks a bit tricky. To do the same thing, we need far more money, and typically VCs have money. So we said, let's start a company, and let's do the full stack of AI. Let's actually build Indian language large language models. Let's build even better speech models, and let's make a voice plus LLM stack that we can use across applications. Right? Do you want to do customer care? You can have voice plus LLMs. Do you want to do something like education? I ask a doubt and it clarifies it based on the textbook I'm studying. You can do it with voice plus LLM plus some data, right? So we're calling this Sarvam. Sarvam in Sanskrit means all. It's really an attempt to build for all. Co-founding this again with Vivek. Vivek, I suppose you are there. Good. Vivek is, by the way, quick introduction. Do you want to introduce yourself, Vivek?
No, yeah.
Okay.
The last 13 years, I've been involved in various things, various national scale projects in India. I've been in Aadhaar for almost 13 years, advisor to UPI and all various other things, GST. So they're going to actually have, for being unemployed for 13 years to actually starting a company is quite a change. But I think this passion for doing things for Indian languages is what has brought me to this. And I think that we can do this. And that's really, if we want to actually say, this is a new technology and India can be at the cutting edge of this technology, and I want to be part of the solution to make that happen. And I think that's really what we want to do here at Sarvam. While it's very much a company, it's also a mission. And I hope we can convince a lot of you guys to be part of this story.
Great. So the mission statement is a bit of a pitch. It also drives the thinking, which is that I think, frankly, Geo changed the landscape last decade, right? They took us from being nowhere in data consumption to being one of the leaders in data consumption. It led to a bunch of things happening, of course, combined with Aadhaar and UPI and so on. I think this decade we should really do that for AI. I think India needs the scale that we have. We don't have enough doctors, we don't have enough teachers. AI is here. It will take 5-7 years to build this, but you can actually build things which are at the unit cost possible for Indians to pay and bring them tremendous value. India pays for education. India pays for things like that, and you can actually make it work better with this. Happy to chat. I'm around for the next hour, so happy to chat with folks. Thank you.
Do you want to take 3 questions? Next 5 minutes?
Yeah, 3 is a good number, I said, yeah. Yeah.
So, why do pre-training yourself instead of just using open source LLMs and then applying your own translation or voice models on top of that? Why do the whole thing instead of just taking what has been done, let's say in North America, and then translating that for Indian languages?
We should do that as step one. As step one, but that's a technical question. How do you add language as a skill to a model trained on English data? We have some thoughts on that, and we are doing some things. That is step one. Step two, you have to build a model from scratch, because the tokens, I didn't talk about that. If you look at a model, it starts off with embeddings of input, which you do as part of a vocabulary. And it's important that you have representational efficiency in encoding your language. So you want tokens that represent indic words. Today, GPT represents indic words, by the way, as ASCII, extended ASCII, with multiple bytes per character, right? But you can actually break up, let's say India, Bharat, right? It's a Bharata, and each one is multiple tokens. But you can have Bha, which means light, right? You can have Rata, which means something else, right? That notion that you can have tokenizers which are efficient, that leads to efficiency in tokenization. Secondly, maybe it leads to better fluency, right? Maybe it leads to better specialization for these languages. But step one is to leverage existing things. Yeah.
Hi, thank you for bringing out the importance of pre-training. My naive question is around data. So the graph that you brought out where Roberta was trained on different data sets, the D90 for different data sets arriving close to its minima differed. So maybe it's telling something about the way the data is prepared or the way the data is structured. And my assumption would be that that paper, textbooks are all you need. The structure of the data, as you talked about, it is the D90 would arrive at its minima even much faster. So from that point of view, the preparation of the data, what do we learn about that, or how would you think about that?
I agree with you. I think pre-training data can lead to lower D90s. That's what the other two papers show. But to your point, right, that particular graph indicated more the difficulty of the task. So for example, one of the tasks there is NLI, which is natural language inferencing. I'll give you sentence 1, I'll give you sentence 2, I'll ask you if sentence 2 follows from sentence 1, right? Which is a reasoning question. Compare that with something like sentiment detection. Given a paragraph, say it's positive, negative, right? The tasks have different difficulties. And when therefore D90 falls, may be a function of that. What's happened is all of that has gone outside the window, because we are now in model regimes that are much, much larger, where all this has gotten squeezed. All these NLU tasks are now sort of similar difficulty levels, right? But pre-training will play a role.
Yeah. So one of the critical things is evaluation when building RAG systems. So do you think there is a need of building separate fine-tuned models for evaluation these systems, or how what would be the right path to do that?
You want to evaluate a RAG system with a fine-tuned system?
Yeah.
Of course, the fine-tuned system has to be more powerful, right? I mean, you should trust the fine-tuned system to do that. And people have been doing it, right? People have been using GPT-4 to tell you if a particular completion is high quality or not, right? But I think that's just a hack for now, right? We are in this regime where, unfortunately, machine learning systems cannot be evaluated by machines, right? The systems are so good that you need humans to evaluate them, right? And that's why I think as I don't know, you're in a startup, for example, you should be creating benchmark data sets and testing them by human evaluation. And there's some fuzziness to that, but I think it's required, right? Meanwhile, if you have much smaller models and GPT-4 prices are affordable, you could use that. Yeah.
Last question. So for your new startup, are you going to collect exclusive data or create it? Is your data strategy?
Yeah, good question. I didn't tell what we will do. I can just take a minute to answer that. So there are three broad things that we'll do. One is we'll build an Indian language small large language model, right? And that will require unlocking new data. And we believe that the cultural fingerprint of the nation is in YouTube, right? And before that closes, I don't know when that's going to close, we have to scrape that data and you need to transcribe that data, right? That is one. We will unlock other sources of data as well. We are discussing that using these systems, and you just feel natural in using and invoking intelligence, right? The second thing that we'll do is we'll build this is the crazy part. We'll try to build a platform which allows people to build LLM apps much easier, right? And deploy it to a particular channel. And the third thing we'll do is we'll try to build, to make enough money, we'll try to build LLMs for enterprises, right? We'll take data that they have in their enterprises, and there are many examples of them, and we'll build and deploy it for them. One thing that we'll do, which is not out external facing, is in India, we will build a GPT class inferencing system. So wherein you have heterogeneous GPUs, and we build an inferencing system that really brings down the infra costs of deploying it. Because if we don't have that, then the margins just add up. These things are so expensive, right? So at the model layer, at the infra layer, there are a bunch of things to do to make it cheaper. Okay, done. Thank you, everybody.